So want to answer this question, number one, while I continue to get set up here? Go. Half of you should be talking right now. Okay. This is for later. Just put this to the side. This is for later. Yeah, so yeah.
The red is the accumulation function. FYI, make sure you know. Yeah, because see, look, right now the rates are negative, but the red graph is positive. So the blue is helping you think about the rates.
Okay, let's get started. Here we go. So where's Jedediah? Where's Jedediah? Yes, sir. So tell me, how did you answer this question? Where is the accumulation decreasing, and how do you know? Okay, so about negative 1.7 to about 1.2? Okay, I need to turn my pen on, so 1 second. Do you guys agree with what he said? From about negative 1.7 to about 1.2. And how, so what was one reason you know that? Okay. So because the rate is 0 here, that's how you know it was decreasing here? Okay. So we're asking about when the accumulation is decreasing, and you're really focusing on the 0. Is that how you know that it's decreasing, the accumulation? Okay. Okay, again, so what is it about it that makes it decreasing? What is it that you're looking at that you know from that interval from negative 1.7 to 1.2 that it's decreasing? Yes, sir. Okay, so he was talking about the values of the rate. I'm going to stick with the values of the rate. What is it about the values of the rate that you know that it's decreasing starting at 1.7 to about 1.2? Negative, right? So the rate of change is negative, right? So the rate of change is negative. So from here to here, that's the best line I've drawn all day. All right. So here, the F is decreasing because right. Okay. What was another way you could tell that F was decreasing in that interval from about negative 1.7 to 1.2? What's another way besides looking at the value of the rate? Besides looking at the value of the rate, what's another way you can tell that the function is decreasing? Derek, what's that? Yeah, the function's going down, right? So the red graph or value of the function, I'm not showing you, but the function values, the y values on the red graph are going down. We're going down, right? So we're going down. So when the rate is, and this is what we talked about last time, and you worked on your homework. When the rate of change is negative, your function is decreasing. Okay. And that's where the function values of y are decreasing. So we're heading down. Okay, so now second question. Where is the rate of change decreasing? Okay, so where is the rate of change decreasing? And remember we talked last time, there's two ways that numbers can decrease. There's two ways you can have numbers decrease. What are they? Those numbers get less positive or more negative. When values are positive, in order to decrease, they need to get less positive. And if values are negative and they're gonna decrease, they need to get more negative. Okay? So where in this interval is the rate of change decreasing? Go. Talk about it. Wow. Draw enough. Okay, let's see what you guys talked about. Where is Devante Trotter? Where's Devante? Is Devante here? Not here? All right, where's Miguel Marin? Okay, Jake Nidell. Jake, what did you talk about, or where do you think is the rate decreasing? The rate of change is decreasing. From about -3. So like kind of starting from the left. It's starting at -3, the left side. all the way to about 0.2. What do you guys think? Agree? Yeah. Ian agrees. What about the rest of you? All right. So about from there to there. And how could you tell that the rate was decreasing? Okay, so at the beginning, in this beginning part here, the rate is positive or negative over here? And becoming less positive, right? Show it. The rate's positive, meaning if the rate's positive means F is increasing. Rate is positive, it means our accumulation is going up. We're actually truly accumulating, right? But as X increases there, what happens to the rate? The rate is decreasing there, right? So it's still going up, but not as fast. So as X increases, it's still going up, but not as fast until we get to a zero rate. And then after that, now the rate is negative and becoming more negative. So in this whole interval, starting here, becoming less positive and more negative, the rate of change is decreasing that whole way. The rate of change is decreasing that whole way. So what is the characteristic about the original function that you see that characterizes this rate decreasing? So the rate's positive and negative, but it's decreasing the whole way. So what can you say about the original function, the accumulation, when that's true, when the rate is decreasing? So the whole left side of the graph. Okay, so we want to think about X changing. We want to think about this as a dynamic situation. So some of you have heard the term concavity before. It's kind of static, right? So we want to think about this dynamically. As X increases, the rate decreasing is having what effect in terms of the function? Do you see that whole time the function is, think about turning, which way is it turning? Always down, right? It's always turning down. Whether it's on the way up, whether the function, whether we're accumulating on the way up, it's turning down. Whether we're accumulating on the way down, it's turning down. So rather than concave down, let's call this turning down. Turning down because we know that variables vary, right? Variables vary. And so whenever our function, our accumulation is turning down like this, our rate is decreasing. Our rate is decreasing. So then what would that mean for the derivative of the rate? If a function is decreasing, so just think of this as any function now. If it's decreasing, what about its derivative? If a function is, to forget that this is a rate function, it's just a function. If I told you a function is decreasing, what can you tell me about the rate? Okay, one person said it. Right, it's negative, right? And so that's that same principle we've talked about before. So f prime of x is if the derivative is decreasing, then the derivative of that must be negative. That's the same relationship that we talked about before we talked about the second derivative. We said if a function, if accumulation is decreasing, its derivative must be negative. Well, so just consider the rate function as its own function. If it's decreasing, then its derivative must be negative. Right? So this, when the original accumulation is turning down, our rate is decreasing, and the second derivative is negative. Okay? So what does that mean for this part? So tell me about this. What is the rate doing now? Starting from here, what's the rate doing now? The rate is increasing. Increasing happens one of two ways. Increasing can be less negative. So at the beginning, the rate of change is getting less negative, and then more positive. And therefore, it's always, the rate is always doing what? Over here. Increasing. So the rate all through here, increasing, getting less negative and more positive, which means that its derivative is? Okay, more people got it that time. So positive, right? Positive. So over here, starting here, about here somewhere. Now in this part over here, we've got our first derivative is what? Increasing. All right, and then the second derivative is positive, right? Positive. And so how can we talk about the accumulation? What's the accumulation doing when the rate is increasing? So the rate is increasing, getting less negative, more positive, so the accumulation is turning up. Whether it's going down, it's turning up, or it's going up, it's turning up. So that's, if the rate is increasing, your accumulation is going to be turning up like this. And that's when our second derivative is greater than 0. Okay, so we went over that, right? If the rate is decreasing, what can you say about the rate of change of R? What can you say about the rate of change of R? And what can you say about the graph of F? Review. Go. Talk to the person next to you. Okay, where's Jordan Fowler? Where's Jordan? Is Jordan here? Okay, where's Bailey Rich? Bailey. Is Bailey here? Is Bailey Rich here? Connor Simpson. Where's Connor? Connor, tell me. Negative. So if RF is decreasing, then the rate of change of RF is negative. Agree? Right. And that's the derivative of the derivative, right? So the rate of change is negative. That's right. And what about the graph of F? What about the graph of F? Okay. And our preferred way to say that is? No. No. These phrases. I'm glad you said that. These phrases: increasing at a decreasing rate, decreasing at an increasing rate. Get them out of your vocabulary. It's too confusing. Talk about one thing at a time. Talk about the rate of change. Talk about the accumulation. What is it doing? Then talk about the rate of change. But don't memorize these little phrases. Okay? I hope you didn't do that in recitation. Did you do that in recitation? Yeah. It's just too, especially when the function is decreasing. This idea of decreasing at an increasing rate or decreasing at a decreasing rate is very confusing. So we want to separate those things out. So what can we say about the graph of F if the rate of change is decreasing? If the rate of change is decreasing, what can we say about the graph of F? It's this side over here. As x increases, the graph is turning down, right? It's bending downward. Whether it's going up or it's going down, whether F is increasing or decreasing, it's turning down the whole time whenever the rate is decreasing. And that's when the rate of the rate is negative. Okay. So let's just do some summary and move on to critical points here. It's this one. Yes. Okay, so we've been talking about the rate of change of the rate, right? Starting to talk about the rate of change of the rate. And so that's the derivative of the rate of change, or the derivative of the derivative. And so that's why we call it the second derivative. And so all these mastery derivatives that you've done, now instead of just saying the derivative, we can qualify them and say they're the first derivative. So the rate of change of the accumulation function, that rate of change, now we can qualify it as the first derivative. And then the rate of change of the rate, or the derivative of the rate of change, is the second derivative. Okay? You follow all the same rules, right? So all the same rules apply. If you want to find the second derivative, you just start with your rate function or your first derivative, and you apply all the same mastery rules that we had before. Okay? So there's other notations for that. These are all notations that you'll see for the second derivative. Okay? So the first two are different. So the first one's differential notation with the function notation, differential notation with y, and then prime notation with the function and prime notation with y. So these are all mean the second derivative. And what do they tell us about the rate? What do they tell us about the rate? Whether it's what? So knowing that the second derivative is positive or negative tells us that the rate of change is increasing or decreasing. And then knowing whether the second derivative is positive or negative tells us what about the original function? Turning down or turning up, right? Turning up or turning down. That's right. Okay, so just some review here, and just to reiterate that this main idea is really most of the ball game when it's getting a little more complicated now. There's more to keep track of, but it really goes back to the same thing, that when a function's output is increasing, what can you say about the rate? Positive. Okay? So, can you justify that? Can you do a little proof of that? So, given that the accumulation function is increasing, can you prove it? Prove that the rate is positive. All right, and here's a hint. We used M. Okay. Okay, here's your hint. How is M calculated? By the change in y over the change in x. That's your hint. So, how can you get from that a function is increasing to proving that its rate is positive? It's like two or three steps. Your hint is that the rate of change is dy over dx. Go, see if you can do it. Can you prove this fact that we've been taking for granted so far? Okay, so this is a little mini crash course on proofs, right? So you start with what you know, and then based on what you know, you make a conclusion, and then we use this symbol, which means implies, and then you keep doing that until you can come to the conclusion of what you're trying to prove. So anyone think they got this? It's basically 2 or 3 steps like this. Anyone think they can make the chain of deduction that gets you from y is increasing to the rate of change is positive? Yeah.
So if y is increasing,
Yep.
dy is going to be positive because d final minus d initial will equal to positive.
Okay, so yeah, so you got the idea. So how do y final and y initial compare?
Gives you a positive answer.
Okay, so all right, but how does y final compare to y initial? Yeah, you just
Great, y final is
greater, right? Yeah, so you're just skipping one step. Yeah. Isn't this true? Without a doubt, if y is going up, then the final value of y is greater than your initial value of y. And then? Right, since dy equals y final minus y initial, then what would you have to say about that? Right, so if y final is greater than y initial, and you subtract y final minus y initial, you're going to get a positive number. So dy is greater than 0. Therefore, we're done, right? Because, so this is all assuming that y final is going to correspond with a greater x than y initial is going to be a lesser x, right? So dx is all, we always think of dx as positive in the first place, all right? So if the change in y is greater than 0, for a positive change in x, then we're going to get a positive over a positive, and that's going to be the rate of change dy dx is greater than 0. Does that make sense? So that's the connection, right? If y is increasing, a final value y is greater than the initial, and then that change will be positive. If that change is positive, then our rate is positive. Okay, so that's a mini proof, right? And when you going higher up in mathematics means a lot more proofs. Okay, this is what higher level mathematics is about. Is proving things, making logical deductions. So there it is typed out. Okay, what about if the function's output is decreasing? What if the function is decreasing? You know the rate is negative. Okay, so those two facts need to be like, you need to instantly always know those. If a function is decreasing, its rate is negative. If a function is increasing, its rate is positive, and vice versa. If the rate is positive, you know the function accumulation is increasing. Okay, we're not going to, you can do that on your own, prove that. But here it is. This is really like 80% of the ballgame, okay? There's just one more part to this. Yeah, so these facts that we're using over and over again hold true for any function and its derivative. So they holds true for the original function, which we often think of as accumulation, and its rate, the derivative, but it also holds true for the relationship between the first derivative and the second derivative. If the first derivative is increasing, then the second derivative is positive, because it's the rate of the first derivative. And if the first derivative is decreasing, then the second derivative is negative. So it holds, these facts hold for any function and its derivative. So there's one more idea that completes the picture, okay? What if the second derivative is positive? Then we know the first derivative increases, and we said that f turns up. This is increasing, an increasing rate for a second derivative that's positive. And then, same thing with this. If the second derivative is negative, we know the rate is decreasing, and the function is turning down. Turning down. Okay, so there's going to be, the rest of the semester, we're going to post online homework for extra credit, okay? And so every problem that you get correct in the online homework, you get a homework point. Like, so your homework's out of 20. So if you do 20 of these online homework problems, you basically just gave yourself a whole assignment worth of extra credit. And there'll be more than that. Okay? Lots of the web work will be all kinds of different situations and examples of graphs and questions relating to these principles right here. Okay, they're going to come at it from every angle. Give you information about the rate and ask you about information about the second derivative. Give you information about the accumulation and ask about the second derivative. Give you information about the second derivative, ask you about the accumulation. You know, they can come at it from every angle. All right? Increasing, decreasing, positive, negative. Graphs turning up, down, okay? So lots of chance to practice this in all different kinds of situations. All right, so let's look at that. So let's talk about critical values now. Critical values. Okay, so a critical value of a function is any value of x where, okay, first of all, the value of the accumulation or the value of the original function has to exist. There has to be a valid output value for it to be for x to be a critical value. And then here's what makes it a critical value. The first derivative equals 0, or the first derivative does not exist. Okay? So these are the two ways that you can have a critical value. So first of all, you have to have a valid output or a valid value of the dependent variable. Okay? And then if your first derivative, your rate function equals 0, or the rate function does not exist, then you have what's called a critical point or critical value. And the critical value is referring to the value of x, okay? When you talk about a critical value, you're saying the x where this occurs, where that rate is 0 or where the derivative is 0. So the critical, when you say critical value, we're talking about the value of x. Okay, so what can we say about, what can we think about the accumulation? If the rate of change is 0, then what would be true about the accumulation if the rate is 0? What would we say for a rate of change of 0? Yeah, right. We said that. So the accumulation is constant, right? Flat line, right? Flat line. But so if that happens, that can happen just for a moment, right? So we talked about constant functions, right? We talked about constant functions. We get the rate of 0. But this can happen. You can get a rate of change of 0 for just a moment. So for just a moment, it's still the same principle, but it's going to be like a flat line, or it's going to be constant for just a moment. Okay, so we call that a pause. Okay, we're going to call that a pause. So it's going to stop or pause momentarily, either increasing or decreasing. So that's what a function being constant at a moment means. If the function is constant just for a moment, that means before the moment it was either increasing or decreasing, and after the moment it was either increasing or decreasing. So it rested for a moment, it paused. Does that make sense? So it's the same thing as when we talked about the derivative or the rate of a constant is 0. So what does it mean for it to be constant for just a moment? That's what we're talking about here as a critical value. It's constant for just a moment. Okay, so we're going to investigate what difference, there's different situations where you can have this. Different situations where you can be going along and all of a sudden your function pauses for a moment, depending on what's happening before and what's happening after. Okay? So we're going to investigate here. And the first one is what we call a local max. So first of all, I want you to just look at the black arrow. First, just look at the black arrow. What is the black arrow doing? It's really boring. What is the black arrow doing? Yeah, it's just showing x increasing constantly, right? So, and we want to think about x just varying just constantly to make it as easy as we can, as we can on ourselves, okay? Just x is going to increase. All right, now watch the purple arrow. As x increases, watch the purple arrow. It's a lot more complicated, but this is where the local max idea comes in. So what does the purple arrow do as x increases through a moment of a local max? Okay, so how many things do we need to talk about with that pink arrow? 3 things happen. 3 things happen at a local max. What's the, let's see, let's call on you guys. Where's Lawrence? G-Will, Lawrence. What's the first thing that happens with the pink arrow? Goes up, right? So the function's increasing. You're on a roll. What happens next? Pause, right? You see, so watch, ready? Going up. Pause, and then decreasing, right? This is what characterizes a local max. Before the critical value, the function's increasing. At the critical value, we said pause, right? Ready? Watch. Pause. And then after the critical value, decreasing. Okay? So on your sheet there, your first line, you're going to fill this out for a local max. Local max. First thing that happens is increasing. See that? Increasing. So now I'm looking at the static graph there in the middle. And then at the critical value, we get the pause. And then on the way down, or when x is greater than the value, decreasing. This is what defines a local max. This is what defines a local max. 3 things in that order. Increasing, pause, decrease. Okay, so now based on that, I want you to make conclusions about the first derivative. Okay, so all this stuff is stuff we've talked about. If the accumulation function is increasing, if the accumulation function pauses, if the accumulation decreases, what does that mean for the rate or the first derivative? Write down words and then sketch. So we're practicing these relationships, right? We've got first derivative increasing, first derivative pause, function increasing, function pausing, function decreasing. What would that mean for the rate? Each of those things. And then, can you sketch that then? So, words and a sketch for the f prime, for the rate function. Words and a sketch. Okay, where's Kindil? Conwar. Tell me, when the function's increasing, what did you say about the rate of change? Positive, okay? And then when the rate of change, or when the function pauses, the rate of change is 0. And then when the function's decreasing, the rate is negative. Good, right? So you should have written positive, 0, negative. Now, how does that turn out in the graph? So what will the graph look like for the rate? What will our rate of change graph look like? Where's Radislav? Novak? Where? So tell me again. Positive? And then? Keep going down. Something like this. And that's not necessarily a line, because Yeah, we'll just keep it generic. Keep it generic. We know for sure it's going down, then it's 0, then it keeps going down. So it's positive, and then 0, and then positive. Okay, and so then look at the graph of the rate. So yeah, positive, 0, negative. And so what's true about the rate? It's decreasing. Okay, so now I have a function that's decreasing. Doesn't matter that it's a rate function. It's a function that's decreasing. Tell me about its derivative, its rate of change. Yeah, negative, right? So then what would the graph of the second derivative look like? Good. Yeah, just below the x-axis. Like this, right? So if a function is decreasing, then its rate of change is negative. And so it's going to be down there. All right, so when you have a local max, what you have the derivative is 0, and the second derivative is negative. Okay, does it make sense? Okay, now any questions on the first row in your table? Does it all make sense? All the conclusions, please. What is not intuitive to you? I'm not sure what's not intuitive to you. No, it's not. Doesn't level off. Why do you want to? Right. It could, depending on what the max is like. It could be like this. It could be like this. It could be straight. That's why I'm scribbling. That's why I kind of just made it generic. There's no. It could be any of these. So you were saying it's necessarily this. That's not true. That's what I heard you say. That it necessarily will flatten out a little bit, but it could look like this, or it could look straight. All we're talking about is the local max. Is it okay? Yeah. So it's not necessarily this. There are types of local maxes that the first derivative might look like this, where it's actually steeper here, not leveling off, or it could be a straight line through there. Yeah, it all depends on the shape of the graph. This here. So we're saying we don't care about the shape. All we care about, somehow it's going up and then pausing and going down. But we don't care about the shape. And then, so therefore, we know it's positive, we know it's 0, we know it's negative, but that's all we know. Cool. All right, any more questions? All right, now I want to take that strip of the sheet, and I want you to fold it back behind the sheet so you're not looking at it when we do the next one. So we're going to start over. And I'm going to erase. Because what I've seen happen in the past is you can just use that previous answer and write everything down without turning your brain on. All right, so we're going to do it from scratch, okay? From scratch. So local min. First of all, what characterizes the local min? Right? 3 things. You're going to write those down here. By looking at there, so study the pink arrow. This is the local min. You're going to write down what the 3 things are. Okay? And then you're going to conclude about the rate in words and sketch the graph. don't look at what you did in the first one, or else it can become a procedural exercise where you're not thinking. Okay, you're either making progress or you're getting help. Or you're finished, I guess. All right, I guess lots of people are finished. Where's Andre Diaz? Is Andre here? Is Andre Diaz here? Morgan? Julia? Ariana? Arona? Where are you? Oh, right in front here. Great. Okay, so tell me about a local min. What makes up a local min? Looking at the right side here. Not the rate. Just want to know about the accumulation. What characterizes, in terms of the accumulation, what characterizes the local min?
In terms of the accumulation,
Mhm.
the accumulation is negative, and then it hits zero, and then it becomes positive.
The accumulation is negative?
Oh, it's decreasing. I'm sorry.
Decreasing.
Decreasing, and then it hits zero, and then it's increasing.
Okay. Is the accumulation 0?
Well, it's constant.
Okay, right. So we got decreasing, and then what? At the local min, we get a pause, whatever the value is, and then increasing. So that's, according to the accumulation, that's characterized as the local min. Decrease, pause, increase. Okay, and then you want to talk about the rate? You raised your hand. Yeah. Okay, so if the accumulation is, so now, what is a local min in terms of the rate of change? At first we have negative. At the pause, the rate will be 0, and then positive. Okay, graph looks like. Good. Right? Something like this. It's not a sharp point there. Start over. There we go. Okay? And so then, what can we conclude about the rate function in general? What's happening? So, what's happening to the rate through a local min? Where's Randy? Randy. So the whole time, for a local min, what is the rate of change doing? Yeah, so in the vicinity of a local min, the rate is then what? Increasing, right? And so if the rate of change is increasing, then what can we say about the second derivative? Where's Michael Shalaby? Okay, not necessarily constant, but yeah, positive is the important thing. That the rate of change will be positive. It'll always. Okay, what did we say about when you had a second derivative as positive, what did we say about accumulation? The graph. And what happens to the local min? Is it turning up? Exactly what it's doing, right? So in the vicinity of a local min, your accumulation is turning up. It's bending up. Whether it's going down or going up, it's turning up. And so that agrees with what we said before, that the second derivative is positive. Okay, questions on local min? Okay, so there are other situations where you can get the first derivative of 0. These aren't the only two. So when you say a critical value, you have a critical value where the derivative is 0, it doesn't necessarily mean that it's a max or min. There's two other things we have too. Okay, let's talk about those. So yeah, so if you have the derivative equals 0, is a max or min guaranteed? Must that be the case? No, okay? No, remember this. So we have what we call rest stops. So it's kind of like you're driving down the highway, okay? You want to really get to where you're going, but you really got to go, right? So you're driving, and what is a rest stop? The rest stop is where you pull over for one moment, and you do your business, and then what? Do you turn around and go back the other way? No, you keep going, right? You keep going. And rest stops, you can't turn around on the highway and go back the other way. So you're going one direction, you pause or you stop, and then you get back on the highway going the same way. So how is that like this? How can we characterize this rest stop? So use your finger as the arrow, right? So imagine x increasing, use your finger as the arrow. What's it going to do? Okay? Use your right finger to track x, and use your left finger to be the y-axis arrow. And do it, and then come up with what characterizes a rest stop of type 1. So you can put your fingers right there on the page. Did I give you that graph on the sheet? So sketch that graph that I put up there. And then you can use your fingers on the axis and track what's happening with your left finger, which is tracking the y values as x increases slowly. So you're making the animation now with your fingers on the axis. And see how far you can get then. So then the same, again, fold your page over so you're just looking at this. Don't look at the previous one. Start from scratch. Yeah. Well, if you're pausing, then what is the rate of change? Any value, or is that zero? Zero. This is what you have to do.
Oh, it doesn't matter.
Okay, one more minute, and then we'll see how you did. This was good. Okay, so rest stop type 1. How would we characterize that in terms of just the original function f, the accumulation? What's happening to the accumulation that gives us a rest stop number 1? Where's Alexis Webster? Increases, pause, rest stop. You keep going down the road, it keeps increasing, right? So you should have increase, pause, increase. All right, and then where's Evan Johnson? Evan here? Not here. How about Christy Fluter? So the rate of change now. The rate of change, if we got increase, pause, increase, the rate of change will, good. Positive, then 0, and then positive. So how can the graph look like that? How can a graph look like that? Can you draw it with your finger? Right. So it's going to be something like this. It's going to be positive, and then it's going to be 0 just for a moment, 0, and then positive again. Like that. Okay? And so then what about, in order to talk about the second derivative, now we got to characterize that in terms of increasing and decreasing. So to the left of C, we have decreasing, then pause, then increasing. And now we can make conclusions about the second derivative. Tell me about the second derivative. Where's Amber? Burnett? Amber here? No Amber. How about Derek? Okay, and what will that look like? Right, so if the rate is decreasing, its derivative is negative. If the rate is pausing, its derivative, or the second derivative, is 0. And then if the rate is increasing, its derivative is positive. And so that looks like? Yep. Negative, 0, positive. Okay, notice at a rest stop, both the first and the second derivative are 0. Do you see that? Both the first and the second derivative are 0 when you have a rest stop. Okay, and so that means what? This is changing from negative, second derivative is turning down. Changes to turning up. Negative second derivative turning down. Positive second derivative, f is turning up. So there we see it. Turning down, turning up. Okay. And if you want, now you can look at this and you can talk about the third derivative. What's happening to the second derivative? It's always increasing. So the third derivative is positive. If you drew that before I started talking about it, extra credit. Okay. Fold it. Fold your paper. Go, do it fast. So rest stop type 2. In terms of the original function, in terms of the rate, in terms of the second derivative. Okay, check. Here we go. So rest stop type 2 means the accumulation is decreasing, then pause, then keeps decreasing. Means that the rate of change is negative, then 0, then negative. Means it looks something like this. Negative, 0 for a moment, negative. Which means that it is increasing first, then pauses at 0, then decreases. Means the second derivative is positive, 0, negative. Which means overall the second derivative is decreasing the whole time. Oh, guess I didn't write that in there. Okay, any questions on that? So what's the goal of this activity? So it's a little bit to learn these situations. So somewhat of a memorization. So now we've worked them through and then you kind of memorize the situations. But more, it's you're practicing analyzing situations because that's the homework it's going to come to you, and the extra credit, the online homework, is going to come at you, and it's going to be, it's like you're starting all over because they're going to bring these situations at you from all different directions. So the practice that you had analyzing the situations is the most important thing. That you can come to a new situation and say, oh, okay, my second derivative, or my first derivative is positive. So that means the accumulation is increasing, things like that. So you're practicing the analysis. But yes, these particular situations, the 4 situations, are important from a memorization standpoint also. Yeah.
On the graph, the second derivative.
Yeah.